Alright, so I was watching a video about reverse sprinklers, and what we've got here is a sprinkler. The basic premise is that a sprinkler shoots out water from these two angled nozzles, right? Pressure comes up a pipe here, comes out here, accelerates water out in either direction. Now, due to the laws of equal and opposite reaction, obviously something spitting out water this way gets a force this way. So when we turn on this little clock, oh, would you look at that? It starts spinning. Right. So that's pretty self-explanatory and quite expected, I would say. I think most people understand that quite intuitively and quite well. How long is this going to take? Anyway, so yeah, that's what a normal sprinkler does. But now, we do have to wonder as well, what would happen if instead of spitting water out, it were able to suck water in? Right. So, obviously there you saw it going backwards because I reversed the footage. But would that actually happen? You see, it seems like there's been a bit of a debate about that, and that's what the video was covering, is if you have two pipes, but now each of these two pipes is sucking in water. So instead of having high pressure here, pushing water out from each end, we have low pressure here, sucking the water in from each end. What happens? Does it spin backwards, like shown in the reversed footage? Or does it not do anything? Or maybe does it spin forwards in the same direction it would spin if it was pushing water? All three of these options seem to be suggested by multiple physicists and apparently smart people. Now, here's the reason why. So the people that say it would suck water is basically simply saying, well, we have the laws of equal and opposite reaction. This water has zero momentum here, and it's being sucked down the pipe, so it's now got momentum in this direction. And for it to have momentum in this direction, this thing must have momentum in this direction. Yay! So now this thing will spin. Right, because it's sucking the water in. And then the people that are saying, oh no, but it's going to spin in this direction, are saying, oh, well, the water's getting sucked from all these different directions. In fact, it even gets sucked in from behind the pipe here. So if all of that water is being sucked in as well as the water in front, and now the water is all hitting against this back section over here when it stops, isn't that going to make it spin this way? Because the water's hitting over here and accelerating it in this direction. And then there's another group of people basically saying, well, I mean, the water's accelerating in this direction, but it's deaccelerating against this. So surely that should be a net zero, right? Because the water comes in here, comes down to, it stops there. So water starts with zero momentum, ends with zero momentum, therefore the pipe must start with zero momentum and end with zero momentum. Now I saw this, and I was a little taken aback, because it seems like that final group is very close, but they're missing something a little bit obvious. Let me demonstrate it. Alright, so I've replaced our water pumps with some pistons that can retract. They're currently in the extend position. Now, we can imagine that the metal poles at the end of the pistons are our water particles. I just made them nice and tall in our third dimension, just to give them a bit more weight, because otherwise the effects would be negligible. So let's see. Make your predictions. What's going to happen when I push that switch? Obviously these metal things are going to come in towards the center, but what's going to happen to the center? Is it going to stay in the same place because it's getting pulled and it's going to hit there? Is it going to rotate in this direction, counterclockwise, or is it going to rotate clockwise in this direction due to the force hitting this? Well, all of it, except the last one actually. It rotates while the particles are moving, and when the particles stop moving, it stops rotating. To me at least, this seems quite intuitive. It's what should happen. As long as the particles are moving down the pipe, it rotates. And when they hit the center and move towards the center, that rotational energy disappears. It cancels itself out. But see, the thing is, it does cancel itself out, like the third group predicts, but only after having moved. Because obviously these water particles are not in the same position they were in when we started. They're in an entirely new position. Meaning that we have potential for the centerpiece to also be in an entirely new position, which it is. So we can see each time we perform this, each time a new water particle is sucked in, the centerpiece rotates. Obviously it doesn't gain momentum because all of its momentum is temporary. It gains momentum while this particle is being sucked in, and then it stops once the particle has stopped being sucked in. So it's never going to speed up. It always stays rotating at the same speed. But as long as water particles keep being sucked in from the outside, it's going to keep rotating. Because we can think of the water particles being sucked down the pipe as if there were an infinite amount of pistons, always retracting, never extending. Because nothing is reaching out to get the water particles. If something were reaching out to get the water particles, then yes, it would simply oscillate back and forth. But no, the water particles are simply being sucked in, so they gain in momentum and end up in the center and having rotated this thing. So yeah, the sprinkler will rotate, just as the scientific experiment proved. But we don't have to worry about differential speed around the outside of the pipe and vortices in the center to explain why it rotates. Just the law of equal and opposite reactions. No complicated bullshit necessary. Thank you. Oh yes, also a last little thing before I end the video is that one nice and easy way to test whether or not I'm correct about this is to try this with arms of different length. Because from what I can tell, with the speed differential in the pipe and the vortices, the length of the arms should not matter. Whereas with my theory, long arms, we have short arms in this case, means that the water particles move further, meaning that the sprinkler in the center will rotate further. Whereas with short arms, it doesn't rotate very far. With long arms, we can see it will rotate significantly further. Since the water particles are at speed for a longer period of time and are moving a further distance. It means that the centerpiece also moves a further distance. So an ideal setup for this would be basically a curved spiral coming back to right above the opposite side. Something like this. Alright, for real now. Thank you. Hope that was understandable. Hope it makes sense. And correct me if I'm wrong. Goodbye.